Okay, yeah, I'm sorry that I couldn't come today. I really wanted to because I was looking forward to meeting you all. I really like this extra lecture series, but I figure if they're going to have campus rules about staying home when you're sick, I should follow them too. So I'm feeling mostly fine and um, just trying to be compliant, keep everybody safe. So I think next week we'll be able to get together. We have a room and everything, which is really nice. And I guess I'll talk for a few minutes about what this extra lecture series is, although I described it in the announcement videos, to see if you all have any questions. So I even have a slide. I'll just share my whole computer and hope there's nothing too embarrassing there. Announcements. The idea behind this extra lecture series is that you can just learn extra stuff. A lot of these topics were once in 61A, or they were developed for 61A and then got moved out of the course or never quite made it into the course, because you can only teach so much in a semester, except that I like all these topics, so why not add even more? But this is totally optional stuff. It's not going to show up on any exams. It doesn't really do a particularly good job of reinforcing 61A material. It's just interesting extensions. And these are extensions that don't matter a whole lot for future courses or like sometimes they even appear in future courses, at which point you could learn them then. But since they fit nicely into the 61A material, I like talking about them now. And yeah, so in some sense, this is mostly just for me, like a chance to talk about things. It won't just be me, though. I'm co-teaching this with Azad. Are you here? Probably not. I didn't give him much warning. So two of us will work together to kind of fill these weeks with things that we think are interesting, is the plan. If you sit through this one, you're like, oh, this is cool. I'd like to go to the rest of them and learn a little bit more about this material. Then you can enroll in this course, 194-175, which is this. It's numbered 194 because that is the number that the CS department uses when there's no real number for something. We never put this through the official process to turn it into a course. So that's why it has the same number as decals and things like that. And the way you enroll is type in that CCN. So now you know the secret, which is that you have to know the hidden CCN, and then you can enroll. Once you enroll, you need to pass. So enroll if you're going to come. I'm not going to take attendance, but I would expect you to show up. And there are 3 extra homework assignments, which I try to make them fall at times when there aren't a whole lot of other things to do in the course, and they just cover topics from here. Does it count as an upper division course? It does not fulfill any requirements anywhere on campus. It is technically an upper division course since it starts with a number greater than 99. Okay. If you don't enroll, you can still come. That's totally fine. And if you just want to listen, if you want to listen to half of them, if you want to look at the schedule and decide which ones you want to come to, that's fine too. Did I mention there's a schedule? Well, in fact, there is. Let me find it. Oh, it's there. Well, kind of. So if you go to cs61a.org/extra, and I'll make sure there's a link to that somewhere. There's that magic CCN that lets you enroll. Here's the schedule of topics, and some of them have yet to be determined. But hopefully we'll get this filled in the next couple of weeks, so you know it's coming and you can come to some of them. Okay, other logistical questions, otherwise we'll dive in. When we enroll, the grading basis should be PNP, not graded, right? Yes, I think PNP should be the only option. I don't intend to give anybody a grade in this course. There are no exams. It's just for fun. And if you don't know yet whether you want to enroll or not enroll, that's fine. You got a week or two to figure that out. And this is not like a high stakes decision. You know, the fact that this random 1-unit PNP course shows up on your transcript will not change your life in any way, I promise. So, you know, you might as well create credit if you're going to show up and do all the work. But if you don't, that's fine. And we can continue to attend this class through Zoom, right? Yes. So like normally when I don't have a cold, I'll show up to Social Sciences 20 and just start the same Zoom session from my computer. And so you can watch me lecture live, and I'll do my best to actually stay in front of the camera so that you can follow along. I can't promise the Zoom experience will be particularly good. Like if I need to write on a board or something like that, it might not all get captured in Zoom. I'll do my best. And yes, I'll post the recordings to this page, cs61a.org/extra, as they are created. Okay, for those who just joined, welcome. All I said so far was logistics, which is that if you want to enroll, you can. If you don't want to enroll, then don't. It doesn't really matter. You can come anyway. Cool. Oh, where's the Quine lecture? So usually what I do for just for fun problems is that if I have time in the extra lecture series, then I talk about them a little bit. And I kind of forgot to prep, but at the end, if we have time, we can talk about Quine for a minute. But most of the time, I'll talk about it after it's due. So like next week, I can go over a solution and how to get there. Maybe this week I can give you a pointer in the right direction. And that link is wrong. There's no .html. Okay. So let's look at an application of higher order functions, which we talked about in yesterday's lecture. This application, I mean, the ideas here are very old, but the idea of using this as an example of how to use higher order functions is pretty old too. It's one of the examples from the original textbook for this course, which is called The Structure and Interpretation of Computer Programs. We no longer use that textbook because we changed programming languages, and we changed the topic order, and so the course doesn't fit the textbook anymore, but the textbook is still great. So I hope you read it at some point in your life. And here's one of the examples from it, but it's been adapted to how we do things in 61A. And if you've taken a calculus course, then you'll have seen this before. But sometimes calculus is, for me, kind of more interpretable if I can use it for computation, kind of play around with it. So Newton's method is a technique for finding approximations to the zeros of differentiable functions quickly and accurately. So what does it mean? Accurate approximation means you get very close to the actual number. What does quickly mean? Well, it's a computational technique where to find a zero, you don't have to run it for a very long time. Let's remember how it works. If you have a function like x squared minus 2, it has zeros, which are places where it crosses the horizontal axis. So these are x values for which the f of x value is 0. There are 2 of them. Hopefully this all sounds familiar. And the 0 itself is the x value. So in this case, it's square root of 2. So this is interesting because since the square root of 2 is the 0 of this very simple function, this will also give us a technique for computing the decimal expansion of the square root of 2. Like if we can use this method to figure out this x, then we found how to write down the square root of 2 as a decimal expansion. And you can do this for cube roots and anything else that's a 0 of some function you can write down. So in particular, if you want the square root of a, then you have to write down the corresponding function and find it 0, which is that when x is the square root of a, then that means x squared minus a is 0. F of x is 0. Okay, sound familiar? I see some stuff in the chat. Let's see what it is. Oh, people are trying to enroll. Good luck with that. And if you ever have a question as we go, feel free to raise your hand. How's Newton's method work? Conceptually, you pick an initial guess for x, which is not the 0, and then you try to find a better guess, one that's closer to the 0 of f of x. So here we've picked some initial x. We're looking for the x where this function is 0. We've found an x where this function is -12. So we're not at the 0. But the way we improve the guess is to use the linear approximation to the function at this point, which is the tangent line. So we compute the value of f at the guess f of x, so that would be -12. We compute the derivative, so that's the slope of this dashed line, which is an approximation around the point. It's a good approximation. Out here, not so good. But then we update our guess to be the 0 of the linear approximation to the curve, which happens to be this formula, x minus f of x divided by f prime of x. So why would you divide by the slope? That's just how you get to the intercept. So what we're computing is how far we need to move in the x direction so that if we were following this line, we would hit y equals 0. Very simple idea. Bridget.
Hey, so regarding Newton's method, at least from what my understanding is find a derivative. Like if we were to code it, like I guess, like when it comes to like function, will we essentially like would there be like special functions that we could use?
Yeah, so when we do this in code, we'll write f as any function like we would define any function. But then how do you derive it? That's a good question. The way we'll start is that we'll use what we know about calculus to also write down the derivative of the function as a separate function. So you can think of f and f prime as things that we will have to define. But since we know some calculus, we can write them both down.
So essentially it's like doing math, but it's in, you're doing it with code instead.
Exactly.
Okay, thank you.
Excellent question. Okay, so there's the Newton's method update. It's still wrong. This is not the 0 of the curve we're looking for. This is the 0 of the line that's an approximation to the curve. But the idea is that you just do it again. And once you get close, the approximation is so good that you converge onto the 0 very quickly. I think there's like a cool animation from the internet. Let's take a look. Oh yeah. So here's multiple iterations. Start with an x, pick your f of x, follow it. Start with a new x, follow it. Start with a third x, follow it. Oh, now we're close. Now look what happens. The line looks an awful lot like the curve. And so we end up at the 0 as soon as we got kind of close to the 0. And that's really the key feature of Newton's method, is that once you get close, you can find the actual number very quickly. When you're not close, all kinds of crazy things can happen. So this is not a foolproof method for finding all the zeros of a function, but it is a way to get from an initial guess that's pretty close to the actual 0 without a whole lot of computation, meaning not a whole lot of steps in this process. Sandeep?
Yes. So is this for only finding one zero? Because if there's multiple zeros, wouldn't we have to modify the algorithm so that it doesn't get confused?
Yeah, great question. What's an algorithm for finding all the zeros? And because this seems to only find one. And the answer there is that this is still useful as long as you can come up with a set of initial guesses that are all close to the zeros that you want. But Newton's method won't do that for you. You need some other method. I'll tell you how this gets used in practice. Like this is a common way to get very precise estimates of roots. Like if you need not just the first 15 digits, but you need hundreds of digits. And the way you do it is that you have some approximation table already set up that basically tells you about what the square root is of any given number. Like, there's like simple functions to do that. And then Newton's method is used to refine that initial guess, which is already close according to some other mathematical procedure. So that's the kind of application that this tends to get used for. But in principle, it can solve any problem that can be expressed as find the zero of this function, as long as you have some way to start kind of close. Okay. Aman?
Yeah. So if you don't know that the function, if the function has a zero or not, like it could just not have any intersection with the x-axis. Like, is there do you normally like have a stop procedure after like 200 loops or something?
Yeah, great question. So let's say you have a parabola that fully lies above the horizontal axis, so there's no zero. You can imagine what this procedure would do, which is that it will bounce around because you're never close to the zero because there isn't one. And so every time you make an update, you've got this curve here, you follow the line and you end up in an entirely different part of the curve, and you just do that forever. So yeah, in that case, you need to do some kind of extension to the procedure that says when to give up. And there's Newton's method doesn't specify how to do that. Like that's kind of an engineering problem that depends on the application that you're trying to solve. Bridget?
So this might be a stretch, especially since my Calc 2 knowledge is like 2 years old. But I was wondering if you could like use series or Taylor series for this, like especially since it's like iteration based.
I mean, this is a linear approximation to the function. You can have a different kind of approximation, like a quadratic approximation to the function or something like that. And then you could imagine that might help you converge faster. But for each update, it requires more computation. And so it's a good idea from a math perspective to use kind of a higher order approximation. Turns out that from a computational perspective, usually this linear approximation is exactly what you want because it's so fast to compute that you're kind of done right away, and it gives you a perfectly reasonable update. So, the other reason why it's fine to just use a linear update is that if your goal is to just get from somewhere close, like x4, to the right answer at x5, linear approximation is often just as good as a quadratic or higher order approximation.
But it's essentially just faster and more efficient to use linear.
Exactly.
Thank you.
Good questions all around. Let's write some code. Well, first, how will we use it? To find the square root of x, we would write down a function whose zero is the square root of x. So that doesn't mean the square root of x comes out when you pass something into this function. That means when you pass the square root of x into this function, you get zero. So the property of this function is kind of backwards. It's not about what output you get for an input. It's about, we know the output already, zero, and we're trying to find the right input that gets us there. And once we find it, we will have found the square root of 2. We need to know how to differentiate. If you've taken calculus, you'll know that this function's linear approximation at any point is 2 times x. And then we're going to write a function, find 0, that takes in these two functions So there's something higher order and gives us the 0, which will be the square root of 2. And once you have this function find 0, you can solve all kinds of other problems. The cube root of 729 is just write down a function whose 0 is the cubed root of 729, write down its derivative, find the 0 of that, and you'll find that 9 times 9 times 9 is 729. Okay. Let's just focus on square roots, then we'll do the general version of find 0. So we're going to try to build up to it. Here's how you find a square root. Iteratively refine a guess x about the square root of a. So our goal is to find the square root of a by guessing and then making our guess better. Where every time we take the existing guess, so maybe it's 1 at the beginning, and then we come up with a new guess, and the new guess is always x plus a divided by x divided by 2. Where did this formula come from? Well, it came from long ago. It's called the Babylonian method, and it's been known as a way of finding square roots for thousands of years. So let's write down this function and see what it does. If you can't see my screen or something, please let me know. Square root of a. What do? We start with some initial guess. While it's the case that we have not found the square root of a, well, how would we know if we haven't found the square root of a? We could square x and see if it's a. While x is not the square root of a, because if you square it, you don't get a, perform the square root update, which was that formula I just showed, which involves both x and a. And then, once we have found an x, when you square it, you get a, you're done. What's the square root update look like? Sorry, I got to rearrange my screen here. It's just x plus a divided by x divided by 2. See if it works. Square root of 9 is 3. Square root of 4 is 2. What is going on here? Let's check it out. There. Let's see what's happening. So when I compute the square root of 9, it's starting with a guess of 1, not right, so it guesses 5, so then it guesses 3.4, so then it guesses 3.02. Now we're close. This is the interesting part of this kind of iterative technique, is that it turns out once you're close, you get much closer very quickly until Python can't even represent the difference between where you are and the right answer, and so it decides that it's done. Where should you start? Well, I don't know. We started at 1. How do we know when we're done? Well, we have this criterion. X squared doesn't equal a. And what happens when we compute the square root of 2? What happens? Uh-oh. It's still running. Stop. Why is it still running? That looks kind of like the square root of 2. Isn't it the square root of 2? Oh no. It's the square root of 1.999999999. So we still need to come up with a way of stopping that will let us give up when we're awfully close and we're not making any progress. But before we do that, let's look at cube roots. How do you implement a cube root? Well, it turns out that there's a method for this, which is start with a guess x about the cube root of a, and then run a slightly different update. So we want a number where when you take x times x times x, we get a. And then we're done. And the cube root update is that formula that I just wrote down. 2 times x plus a divided by x squared all over 3. Have we written down something that kind of works? Root of 27 is 3. That's good. Cube root of 64 is 4. That's good because 4 times 4 times 4 is 64. Cube root of 2 actually worked. This times this times this is 2. Cube root of 3. Oh, here we're stuck in that problem where we got awfully close, but we didn't finish. If you'll notice, the code for square root and cube root are identical, except for some expression that checks whether we're done and the update itself. These are both instances of Newton's method. Instead of repeating ourselves by writing the same code twice, we should use higher order functions to encapsulate the notion of how are we done and the notion of time to make an update. And then we can worry about the problems like, how do we stop when we're really close just once instead of twice? Because right now we'd have to like code it into here and code it into here, but it would be better if we just wrote that down once. Okay, questions, Aman.
So I was wondering, what would you consider the complexity of like this method to be, the computational complexity?
This is so computational complexity usually deals with algorithms of, like when you're first introduced to it, it deals with algorithms on discrete structures, and you can count up how much work there is to do. This is about the number of iterations it takes in order to get a numerical approximation that is within the correct answer by some epsilon. So the computational complexity of this isn't about how long it takes to run based on the problem size. It's how long it takes to run based on how close you want your answer to be to the correct 0 of the function. And it is root n in the number of digits. So computational complexity is something we'll talk about a little bit in this course, a lot in 61b, and then you refine your understanding of it in later courses like 70 and 170. And so it's great to wonder about these things now. And so I'll give you a little flavor of like the efficiency of the algorithm. But if you didn't understand any of that, that's totally fine because it's something that you'll deal with later on in the curriculum. But yeah, that's basically the story is that, and you can actually kind of see it happen if we put our prints back. Oh, I'm sorry. I stated it wrong. I said that it was root n in the number of digits you want, but it's actually log n in the number of digits you want. So basically, the number of digits that's correct will double every time you run an iteration.
Okay, thank you.
Okay. So, Prajeet.
So is there, in terms of like, if you're like find like higher powers, like for instance, like, I don't know, quad or like fifth. So if I'm getting this right, like, would we just have to like, for like the denominator, just multiply like an additional x and then increase
Yeah, good question. So it's like we did square, quadratic and cubic. Isn't there some formula for the quartic or whatever? And we will generalize this very soon. And it won't involve knowing the formula. It will just involve having, you know, Python figure it out for you.
Mm-hmm. Perfect.
Sasha.
Thank you.
Hi, Sasha.
Hi, John. Thank you. What's the benefit of starting at 1 versus randomly as in Markov chain?
And good question. There's no particular benefit. It turns out like it doesn't really matter that much where you start for the case of square roots and cube roots. So I just picked a convenient number. Okay, so we still have to solve these same two problems. Where should we start? Well, 1 actually is fine. How do we know when we're finished? There, I think we have to do some work, and we should be able to do it just once. So instead of writing down square root and here's how you do it, and cube root and here's how you do it, I'm going to write down how you take a guess and improve that guess using a function that tells you how to update it, a function that tells you when you're close to the right answer. You're so close you might as well stop. And some initial guess, which will start out at 1. And this is a very general notion, which says, well, we're not close to the right answer. So close tells us whether close to the right answer. Guess tells us where we are now. We'll come up with a new guess. I did it wrong. Which just involves taking the current guess and improving it to get a new guess. And then when we've improved it a bunch of times until we're now close, we return the guess. We can edit this function if we need to, but let's first express the notion of square root in terms of improvement. The way we'll do it is by writing down 2 functions. An update function, that's pretty simple. We call square root update on whatever the current guess is, x, and the original a that we're trying to compute the number from. And how do we know we're close? The original one was check whether x times x actually equals a. Then we're close. Then we're actually there. How do we compute square roots? We call improve using this update function and this close function. Now I think we've achieved the same behavior that we had before. We can compute the square root of 4. Nope. I spelled it wrong.
I think someone had commented about how in the improve method you have like guess is equal to improve guess, but did you mean like update or another method? Because improve only takes 2 args. Okay.
Thanks. This is why it's so nice to lecture live, so you fix all my bugs for me. Okay. We still have this problem. We can't compute the square root of 2. So let's fix that one. Instead of saying x is times x is a, let's say, well, it's approximately equal to a. And we need some notion of approximate equality. So let's write that down. When is y about equal to z? There's lots of numerical ways to express this, but I think a simple one is to just take the difference between y and z and make sure it's really small. We use the absolute difference so that we don't have to worry about which one's bigger. And we say it's less than some small number. How about we come up with a default that's 1 times 10 to the negative 15. That's in scientific notation, which works fine in Python. And hopefully, type.
I think your function name is different. In the first function, you say approx, and then you define it as approx.
And close. Square root of 4 works, and the square root of 2 now gives me something reasonable. It's right except for the last digit, and so it's close enough. Now that we have these notions, we could rewrite cube root as well. Return the result of improving an original guess using an update function, which is the cube root update for x and a, and a function that tells you whether you're close, which is to make sure that x times x times x is approximately equal to a. Cube root of 27 still works, cube root of 64 still works, but now I can take the cube root of 2, which gives us some number that's awfully close to the cube root of 2. Oh, that one always worked, didn't it? Cube root of 3 works too. Okay, so here's just an example of how you could write things where you give functions names, and any name would have worked. This could have been, instead of update, something else, as long as we were consistent. Or we could use anonymous functions using a lambda expression, which does the same thing, creates a function. Except for this function's a little bit different because it uses cube root update instead of square root update. I think we're ready. Write down Newton's method. Oh, there's a hand up. But let me write this down and then we'll do questions. How do you find the zero of f and you know its derivative? In general, you have to know when you're near zero. And how do you know when you're near the zero of a function? When it's approximately equal to the following two values. F of x, we don't want x being zero, we want f of x to be zero. That's what it means for x to be a zero. Has to be close to zero. How do you find the zero? You guess until you're close. That's Newton's method. Using the Newton update. For f, you need to know its derivative. And then improving not only requires an update, but it needs some way to know that you're done. Which, by the way, is near zero. What's the Newton update? You take a function and its derivative, you come up with a new function that takes in a particular x, and you want to come up with a better x, and the better x follows from the formula that we wrote down on the first slide. So that shifts from the old x to the new x. Now we can rewrite square root. Instead of having an update and a close function, square root, all it really needs to know is what's the function whose zero is the square root of a. X times x minus a. What's its derivative? Times x. Now we just find the zero of f and df, and we should get the square root of a. Moment of truth. Fine, works fine. Notice that we didn't use this magic formula anymore. We don't need that magic formula anymore either, because all we need to do is write down the right functions. What would the right functions be for cube root? We would find the zero of x times x minus a. And we need to know enough calculus to be able to derive that. So what's the derivative of x cubed? It's 3 times x squared. So can we find the cube root of 27? Yes, we can. And the cube root of 3 works too. And how's it working? Like, where's the actual updating happen? It's happening here in improve. Here's where we had a guess and we come up with a new guess. So when we're computing a square root of 4, we're actually getting, a bunch of different guesses along the way. And they are in fact, start out pretty wrong, and then once you get close, you finish. It's actually just doing the Babylonian method, except for expressed more generally as a way of finding zeros for any function. And that means if you wanted, you could write down the nth root of a or any polynomial. Here you need n. So like for the square root, you'd have n equals 2. And for the cube root, you'd have n equals 3. But what about for the nth root? You just write it's the number that when you raise x to the power n, you get a. So x to the n minus a equals 0. And do we know enough calculus in order to derive that? I think we do. Bring the n down, subtract 1 from it. Then we would just find the 0 using f and df, and I would get the nth root of it. So what's the square root of 9? 3. And what's the 6th root of 64? 2. So now I don't even need this. Nth root of a using 2 as n. This uses 3 as n. And I finished my implementation. I've written down what it means to improve things. We don't always need to print the guesses out along the way. We've written down what it means to be close enough that we're done. We've looked at how to find a 0. We've had that one magic formula, the Newton's update. And then if we want to find roots of numbers, which is an application of Newton's method, then we need some way of coming up with the f and the df. Okay, so why is this an interesting application of higher order functions? There are several cases where you have a function returning another function or a function taking in functions as arguments. It's just a very nice way to separate the details of the implementation, like how we're defining approximate equality and which route we're taking, from the functions that we wanted to implement in the first place, which are square root of a and cube root of a. And this is very extensible. We could have the 4th root of a as a function as well. So usually at this point, people look at this and they're like, this seems to kind of make sense at a high level, but this particular part makes no sense to me. If it makes no sense to you, it probably makes no sense to many other people here. And so I'd be happy to describe individual parts of this if you would like, but you have to let me know. Okay. If there's no questions, you can ask questions later. If you're like in the middle of typing a question, it's totally fine. But I figure I'll address the one annoying thing about this implementation, which is that we need to know how to differentiate. And what if we don't know how to differentiate, or we want the computer to do it for us? Well, we could approximate that in the following way. Differentiation, so far we've been doing it symbolically. Like we've known that the derivative of x squared is 2x, but it could also be done numerically. The way you do it numerically is that you look at the definition and you approximate this limit by using a really small a instead of actually looking at what a does as it goes to 0. So the definition of the slope of this line is just the change in f of x over the change in x, where a is the amount of change. And if a is a really small number, then you'll get some like reasonable approximation to this slope. If a is big, this won't be a very good approximation, but if a is small, it'll work out pretty well most of the time. So the idea here is just like pick some point nearby, draw a line through that, and you've almost drawn the same one. Once you have that concept in your mind, you can write it in code. What's the slope of f? at x, where you have to pick some a. We're trying to pick a small a. How about 1 times 10 to the negative 10th? Why that? I tried it earlier, it worked well. Then you just divide the difference between f of x plus a and f of x by a. That's how you get the slope. And now you have some notion of approximate derivatives. So how do you derive a function f? Well, for any x, you get, or sorry, this should be differentiated. A function f. For any x, you want to get the slope of f at x. That's differentiation. So now instead of finding 0 requires f and df, we could have find 0 that just takes f. And now we need a df. How do we get it? We'll just differentiate f. Oh, we don't need u anymore. We don't need u anymore. And can we still compute the square root of 2? Yeah. So now the square root of 2 involves computing the nth root of 2 for n equals 2, which just writes down the function whose 0 we want. And finding 0 figures out an approximation to the derivative that's good enough that you get the same answer, and uses that in order to compute the Newton number. The lack of questions is alarming. Maybe it just needs to sink in. I just wanted to show you, like, we're not going to do a bunch of numerical computing in this course, but it is an interesting topic where you have to think about like how you're going to compute the answers to, real valued questions like this one. This is a general technique that gets used in a lot of different cases. So now you know it exists. I mean, probably from calculus class, you knew it existed already. But now you know it exists as something you could implement. And mostly the implementation is just translating ideas from math into code, and higher order functions can help you do that pretty succinctly. Come on.
I don't know if this is like a bad question just because I am kind of new to lambdas, but when you, in the differentiate method, when you said like lambda x is the function name, right? So how can you?
Yeah, so let's do a little translation. Every time there's a lambda x, you could have written it a different way as a def. I would have to pick a name for it. This x is that.
Okay.
This expression is that return value. And then I would have returned df.
Okay.
Oh, it's just a comment. So this isn't doing anything, but I just left it there so you can see it.
Okay.
So yeah, I mean, if there's a case where the only reason you gave this thing a name is so that you could just return it or so you could just pass it in, then that's a reasonable situation to use a lambda, because we didn't really need to name it. It was already named pretty well because we knew we were differentiating. Rajit?
Oh, so this is sort of a general question about lambdas, but so I know like we have all this code, but couldn't we just run some of the code with lambdas? Like, is there any like disadvantages of using lambdas per se?
There's no computational advantage or disadvantage to using a lambda expression instead of a def statement. It's purely whether the code is easier to read with it or without it. If you're new to lambda, then everything with a lambda in it is going to be harder to read. But as you, Yeah, as you get used to what it says a function that takes x and computes the slope of f of x, then you can have very natural definitions. Like, so once you're comfortable reading this, then you can say like, oh, does this look right? It says to differentiate f, what you do is you return a function that takes in x and gives you back the slope of f at x. Oh, that must be right, because it's basically exactly corresponds to the mathematical definition. So that's the advantage of lambdas, is that instead of having to break it up into 3 lines and give this thing a name, instead we can just say what it is. It's a function that takes x and computes the slope.
So basically the composition aspect of it.
Yeah.
I was asking because I did lambdas in Java, so I was wondering if it was similar to that, like in Python.
Yes, in Java, there's support for anonymous functions, and all the same suggestions apply, which is that they don't change the power of the language in any way. They just change the way in which you can write what you want to say without introducing extra names that you don't think you need. But it's not like you should avoid giving functions names. If it's helpful, give it a name. Like if it was helpful to call this thing df to understand it, then this is better. I mean, in my opinion, it's not really helpful to give this thing a name because you already know what it's going to do.
All right. Yeah. Thank you.
And, the same might be true for here. We called this thing f, but maybe that's not helpful. Maybe the easiest way to understand this is just to think, well, I need to find the 0 of a function that is x to the n minus a. So then I would write it's a function that takes x to the n minus a, and that's the whole definition.